So I'm going to introduce Semiretti's regularity lemma. So this takes some definitions. So first, let me define what an epsilon regular pair is. So let's consider two sets of vertices A and B that are disjoint in a graph. We say the density between A and B, it's D of AB, is it's the number of edges from A to B, so it's just the number of edges with one end in A and the other end in B, and you divide that by the size of A times the size of B. So the density is always between 0 and 1, or, well, not strictly between it. The density can be 0 or it can be 1. The density would be 0 if you have no edges from A to B. The density would be 1 if you have every possible edge from A to B, because if that were the case, then the number of edges would just be the size of A times the size of B if you had every possible edge, and then you'd get a density of 1. In general, the density it's what it sounds like. You know, there's a reason why we use the word density for it. It's the proportion or the fraction of edges that are there out of all of the edges that could conceivably be there. Okay, and we say that AB is an epsilon regular pair if we have the following. For every subset of A and subset of B, so I have A prime in A and B prime in B, and these subsets are not too small. We have some parameter epsilon that's a positive number, but we're using the letter epsilon because the idea is that epsilon is going to be smallish, and A prime can't be too small, so it can be fairly small compared to A. Like we're thinking of epsilon as a small number, but A prime can't be too small, and B prime can't be too small. And whenever that's the case, we have that the density between A prime and B prime is close to the density between A and B. In other words, if I take the difference between these two densities, that difference is less than or equal to epsilon. So yeah, that's what an epsilon regular pair is. And roughly speaking, the motivation behind this definition is to just make sure that the edges between A and B are sort of scattered around, that there's not too many edges in one place, roughly speaking, and then no edges in other places. That everywhere you look, roughly speaking, once again, everywhere you look, you see about the same density of edges. That's the motivation behind a definition like this. And yeah, so by the end of this video, I intend to actually state Semiretti's regularity lemma, but so far I just have a definition. The regularity lemma, roughly speaking, is going to be some assertion about how such things exist. But before we get into what the lemma actually says, let's talk about some of the power that it has. So here's a proposition. So suppose AB is an epsilon regular pair with density D, and sorry, this is so small, but let B prime be a subset of B, and B prime isn't too small, so the size of B prime is at least epsilon the size of B, right? So, okay, then the conclusion is that the number of vertices in A that have less than this many neighbors in B prime is at most epsilon times the size of A. So what is this really saying? Maybe I'll point to this picture. So I have some A prime in here, and B prime in here. And D is the edge density. And again, the edge density is like the proportion of edges that are there. And intuitively, we can kind of think of D as the probability that an edge is there. I mean that there's no randomness in what we're talking about, but we can intuitively kind of think of this proportion as a probability. And if I pick a vertex in A, oops, yeah, sorry, there is no A prime in this. So yeah, never mind. If I just pick any vertex in A, and I look at how many neighbors it has in B prime, how many neighbors do I really expect to see? Well, if I just pick a vertex in here, there's the size of B prime, many possible edges that could go into B prime. And then we have this proportion D that's telling us the proportion of edges that are there, roughly speaking. So I would expect out of these B prime many possible edges, I would expect a proportion of D of them to actually be there. And this is almost saying that. It's not saying that a D proportion is there. It's saying D minus epsilon. We're giving away a little bit. Epsilon is like an error term. And so what this is really saying is, once again, when I look up at this picture, intuitively, if I'm not being very technical and being kind of sloppy, if I'm looking at a vertex here and saying how many edges should it have into B prime, it quote unquote, it should have about D times B prime. What we're saying is the number of vertices in A that do significantly less than that, meaning that they don't get D times B prime many neighbors. They don't even get D minus epsilon times B prime many neighbors in B prime. The number of vertices in A that get less than that is not very much compared to the entire size of A. This is like hardly any of the vertices in A. This is a small proportion of the vertices in A. Similarly, there's a part 2 that is just talking about vertices in A with too many neighbors in B prime. Once again, a vertex in A intuitively should have D times B prime many neighbors. So there shouldn't be very many vertices in A that have D plus epsilon times B prime many neighbors in B prime. And part 2 just says that the number of vertices in A like that is also at most epsilon A. The proof of this is straightforward. You just let A prime be the set in A. It's the set described in 1. In other words, A prime is the set of vertices in A that have fewer than this many neighbors in B prime. And suppose, for the sake of contradiction, that you have more than this many vertices. We're trying to prove that A prime is at most epsilon A, so assume for contradiction that it's not. Then, well, we can calculate the density between A prime and B prime, or I shouldn't say calculate, we can upper bound it. Because, so what's the density between A prime and B prime? Well, it would be the number of edges from A prime to B prime. And each vertex in A prime has at most D minus epsilon B prime many neighbors in B prime. So if I'm adding up, if I want to count all the edges from A prime to B prime, I can just go vertex by vertex in A prime and just add how many edges does it have, does that vertex go into B prime. And for each one of those, that answer is at most d minus epsilon times B prime. And if I add that up for A prime many vertices, I'm going to get this number of edges on the top, or at most that number of edges on the top. And then I would divide that by size of A prime, size of B prime, and cancel some stuff, and I get d minus epsilon. So the density from A prime to B prime is less than d minus epsilon. But that's too far away from D, right? In order to be an epsilon regular pair, the density between subsets A prime and B prime, it should be close to D. D is the density between A and B, so this should be close to D, and this is just too far away from D. The difference between this and D is going to be larger than epsilon. And that's a contradiction. Once again, to be an epsilon regular pair, this only has to be true for A prime and B prime that are big enough. They can't be too small. But part of our assumption, for the sake of contradiction, was that A prime wasn't too small, and then that's why we get to apply this. So, oh, and by the way, part 2 is entirely similar. You just let A prime be the set of bad vertices that have too big of a degree, and you calculate the density, and you get a similar contradiction. Okay. Let me do something along a similar vein, because what we're really going to use the regularity lemma for is to find subgraphs. This is, like, if you recall, we're doing extremal graph theory right now, and we have been talking a lot about if a graph has at least a certain number of edges, then it has to have a certain subgraph. And we're going to use the regularity lemma as a tool to find certain subgraphs or show that they exist in other graphs. So let's do something that is approaching that. Let D be greater than 3 epsilon, and epsilon's a positive number. Then for sufficiently large n, whenever AB is an epsilon regular pair of density D with A and B both have size n, the graph contains K22 as a subgraph. Right, I said we were going to use this to find subgraphs, and for some reason I'm picking on K22. I'd like to talk about how to find K22 as a subgraph in various things. And just to illustrate, of course, all of this is just assuming that A and B are part of some graph. Of course, that graph might have more vertices that aren't in A or B. I'm going to find a K22, and to be really clear, I'm going to find a K22 that looks like this. There's going to be 2 vertices in A and 2 vertices in B, and it's going to look like this. It's not going to involve any of these other vertices that might be in G or anything like that. So that's the intent. So, right. I'm going to use what we already proved. I'm going to let A prime be the vertices in A that have at least D minus epsilon B neighbors in B. In other words, I'm going to basically cut out some bad vertices in A. The vertices in A whose degree into B, the number of neighbors into B, is too far away from D, or too far away from D times B. D times B is what it sort of should be if the intuitive density holds. And we just showed that, right, the number of vertices in A that have smaller than that degree into B. I guess I'm setting B prime equal to B in this application of the proposition. But the number of vertices in A that have less than D minus epsilon B neighbors in B would be at most epsilon A. So that's that, and I'm letting A prime be the vertices that don't have too small of a degree, that they have degree at least D minus epsilon times B into B. So A prime would then be at least A minus epsilon A, which is like 1 minus epsilon times N. Okay, now I'm just going to arbitrarily choose a vertex in A prime, just V. And then I'm going to let B prime be the neighborhood of V in the set B. And of course, since V was chosen from A prime, and A prime is the set of vertices with at least this many neighbors in B, the degree of this vertex is at least D minus epsilon times B, and B prime is its neighborhood, so B prime is at least that big, which is D minus epsilon times N. Now I'm going to let A double prime be the subset of A prime, which is the vertices with degree at least this into B prime. So I want the vertices, what am I talking about? It's like another application of this is really what we're doing. With this B prime. So this would say that the number of vertices in A with less than this many neighbors in B prime is at most epsilon A. So I have my set A prime here, which is A prime is at least this big. It's at least this big, right? And now I want to possibly exclude more vertices. I want to find a subset of A prime, A double prime. And that's the set of vertices that don't have too small of a degree into B prime. But by this previous proposition, I know that out of all the vertices in A, the number that have too small of a degree into B prime is at most epsilon A. So there's at most epsilon A many vertices in A prime that would not be in A double prime. So the size of A double prime is at least, I'll just take the size of A prime, and then I'll subtract the bad vertices from A, in other words, the ones that have too small of a degree into B prime. And that's at most epsilon A of them. And then I know what I know about the size of A prime, and then I'm subtracting another epsilon A. So this is basically 1 minus 2 epsilon size of A. And meanwhile, I'm almost there, right? Because I've got my two vertices on the left, and I've got B prime and V is adjacent to everything in B prime, U isn't adjacent to everything in B prime, but as long as U is adjacent to at least two vertices, like as long as I can find two vertices in here, then V is adjacent to both of them and U is adjacent to both of them. As long as U is adjacent to two vertices in B prime, then I'm done. Oh, and by the way, yeah, I forgot to say this. U is just an arbitrary vertex in A double prime, in case that wasn't clear. And A double prime is the set of vertices with at least this many vertices in B prime. So basically, I just need this to be at least 2. And once again, I just need U to have at least 2 neighbors in B prime. And this is where it comes in, where I said technically that this is only true for n sufficiently large. So I have to look at what we did. I have to say, U has at least this many neighbors. I need this number to be at least 2. And the truth is D and epsilon might be very small numbers. The only thing we assumed is that D is greater than 3 epsilon, which is greater than 0. And yeah, by the way, the assumption that D is greater than 3 epsilon comes in. In fact, I guess I'm not sure why we need 3 epsilon. The 3 may be a little bit arbitrary, but for example, in these places where I'm talking about D minus epsilon, I want that to be a positive number, obviously. So since D is comfortably larger than epsilon, this is a positive number. And since I'm just claiming this about n sufficiently large, and this is a positive number, if I take n sufficiently large, this number will be greater than or equal to 2, and so this vertex will have at least 2 neighbors in there. So that's the proof, and I guess maybe the surprising thing about this is that it can work for small d, as long as d is greater than 3 epsilon. Like so then epsilon would have to be small too, but d can be small, and it's amazing that we're able to get the edges to line up this way. We're able to find 4 vertices that where the edges come together just right among these vertices to make a K22, despite the fact that the edge density could be small. By the way, if we did the same proof more carefully, the proof, it's pretty clear in this proof that this proof can be pushed a lot farther. For example, we just needed this, in the end, we just needed this set to be size at least 2. If we found 3 vertices in here, then we would find a K23. If we found 5 vertices in here, we would find a K25. And it's clear that for n large enough, we would find that. Also, we had a lot of choices. We had potentially a lot of choices for U and V. Like A prime, V was just an arbitrary vertex in A prime. And A prime had this almost n vertices in it. So if I wanted to count the number of K22s, roughly speaking, I would have to take into account how many choices for V I would have, and then how many choices for U I would have. And the answer is kind of a lot. And I'm not going to do this in detail, but if you run through this carefully, you'll find that the number of K2s is at least, roughly speaking, the number that you would expect in a random graph, where when I say a random graph, I mean where we treat each edge as if it's there with probability D. because D is the edge density. So if you can follow this, this is a bit intuitive. This isn't formal really, but if this were a random graph, how many K22s would we expect? I would do n choose 2 to choose 2 vertices on this side. I would do n choose 2 to choose these 2 vertices. And then what's the probability that these 4 edges are there, these 4 edges? That would be d to the 4th if the edge probability is d. And this would be, yeah, so I told you this wasn't formal, so maybe this I should write approximately here. N choose 2 for large values of n. N choose 2 is about n squared over 2. So this is about n squared over 2, n squared over 2, d to the 4th. So this is approximately 1/4 d to the 4th, n to the 4th. And what I'm claiming is, if we ran through this proof carefully, we could show that the number of K22s is almost this big. More technically, what we would get is not really this, but it would have an epsilon kind of error term, meaning instead of this, I would have like 1/4 d to the 4th minus something that depends on epsilon. Maybe this is like a 10 epsilon or something here, but there's some error in here that is negligible if epsilon is very small, but there's some error in here. So I guess why I'm talking about this and what I'm getting at is epsilon regular pairs, they in many senses, they do behave similarly to a random graph, and in the sense that if you're trying to count how many K22s appear, the answer that you get will in some ways resemble the answer that you would get in a random graph. Okay. So then let me just finish up by actually stating the Semireti regularity lemma. So, yeah, I guess I'll just get into it. For all positive epsilon, there exists a capital M and an N naught, such that for all n greater than n naught, and if you have a graph with n vertices, there's a partition of the vertices into t plus 1 parts, so you have v naught through vt. Then you have, and they satisfy the following properties. V naught is not too large. V naught is less than epsilon n. The rest of them are all the same size. The number t is not too large and not too small. Specifically, it's in between these. And almost all of the pairs, if you look at the pairs VI, VJ, for distinct I and J and excluding 0, so I and J are both at least 1 and they're different, and you look at those pairs, almost all of those pairs are epsilon regular pairs. And when I say almost all of them, I mean all but at most this many, epsilon t squared. So the number of these pairs that are not epsilon regular is at most epsilon t squared. And this is hardly any, because the number of pairs total that would be like this would be t times t minus 1, because you have t choices for v sub I and then t minus 1 choices for v sub j. T times t minus 1, for large t, that's basically t squared. And so there's roughly t squared many such pairs, and we're saying that the number of them that aren't epsilon regular is at most epsilon t squared. So that's roughly speaking hardly any of them if epsilon is small. So I drew a picture We often call V naught, we call it the rubbish bin. We're not really having any requirements for the rubbish bin except that the rubbish bin be small. Notice that the rubbish bin is left out of anything claiming that it would be epsilon regular with anything else. So we just have this exceptional set, the rubbish bin. And then we have all these other sets. They're all the same size. And almost all of these pairs are epsilon regular. So, V1 and V2 is epsilon regular, V2, V3 is epsilon regular. I guess they might not be, but almost all pairs are epsilon regular. There might be, maybe V3, VT is not epsilon regular. There can be a few pairs that are not epsilon regular. And I guess the amazing thing about the regularity lemma is that, of course, it's hard to parse all of the order of quantifiers here. There's like a for all there exists, for all there exists. It gets a bit tedious, but it's one amazing thing about this is that like this for all, meaning that this is for all, like n can be arbitrarily large here. So you fix an epsilon, and then based on that epsilon, there exists a number m, and then for arbitrarily large n, I mean, n has to be sufficiently large, but it can be arbitrarily large. N can be very, very large here. It just has to be large enough. That's the only requirement. You can always partition the vertices of any graph on n vertices this way. And this thing here about the number of parts is this is partially what gives this lemma its power, because epsilon and m are basically fixed. You choose an epsilon and then m depends on epsilon, and then n can be any size, and the claim is that you have this partition into t parts, or t plus 1 parts, and t is between these two numbers for any n. And if t were allowed to be too small, like if t were allowed to just be 1, then this would not be a very strong statement, because the regularity lemma doesn't say anything about what's happening within these sets. It doesn't say anything about edges that would have both ends in V1 or edges that would have both ends in V2. The statement of the regularity lemma is all like, the only claim about edges is contained in here, and talking about epsilon regular pairs, that's all about edges between sets. That's not about edges within sets. If t were allowed to just be 1, then I would just have one big set. I mean, I could have V naught be empty, and then I would have V1 be everything, and that would satisfy the conclusion, but it would not be impressive at all because it's not saying anything. If t were allowed to be too large, then this would also not be an impressive statement, because you can always do the partition where every vertex is in its own part, for example, and you would have a lot of parts. You would have n parts, but it would automatically be an epsilon regular partition. Maybe I encourage you to check that. It's a nice sanity check that if you do the partition where every vertex is in its own part, then it it would satisfy this. I guess you let V naught be empty and let all of these be 1. This, of course, would not work because the number of parts would be n, and n is potentially large. N might be larger than m. But it would also satisfy this. In fact, every pair would be an epsilon regular pair. And that would not be an impressive, strong statement. It would not be surprising that that's true. It's surprising that the regularity lemma is true, partly because of this condition too, because the number of parts is not too large and not too small. Anyway, maybe I've gone on long enough about this for right now, so I'll leave this video here.